thank you for setting all this up, Joshua, and to Mia. Where's Mia? Where did Mia go? Thank you. This is going to be a really interesting room dynamic. And I like to pace, so it works well. The problem is I also have demos, so I'll have to kind of walk around and figure out how to use the mic at the same time. So as Joshua said, I'm with this autonomous systems group, which is new to Microsoft, this group. This technology stack is based around a concept called reinforcement learning, but also machine teaching. And how many of you have a background in AI? Or statistics? Yes, okay, machine learning, everything. Most of us, for those of you that raise your hand, imagine that most of you have this background from supervised learning. You know, the whole idea of recognizing images using AI after it's being trained to do some kind of classification of an image or regression. I got to experience this firsthand along with my wife on the way over from SFO for the first time because I just got a Tesla on Saturday, and I am really nervous to put it in autonomous mode. There's a lot of times I was clicking it, and I really scared the pants off my mom because she was ready to buy a Tesla, literally just from this test drive, until I showed her the autonomous mode, and she's like, "No, it's not for me." So I think it's a little hairy. What I found, how many of you have driven in a Tesla or seen this autonomous driving? It's a pretty amazing stack. What I found interesting, because I literally had never experienced it until yesterday and today, was the interaction that's required as the driver and the computer itself. It wasn't like click a button and you just start reading a book and you get to your destination. It was a real interactive thing, and it really enhanced my driving experience where I felt like I knew kind of more about what was going on with the road because of all the features. It was a little unnerving when it changed lanes, but I felt like it would make me a safer driver. And then I missed the exit to the airport. And I was 10 minutes late getting my mom to her flight, and so she's definitely not getting a Tesla now. So about 2 weeks ago, there was a story on Vox. Does anyone know what this is? Like, this was like one of the lead images, and it's important enough for me to show you at the beginning of this talk. It's not Sauron's magic eye. You know what this is. You can't say. Does anyone know what we're looking at? It's 1,000 degrees Celsius. That's what we're looking at. It's 1,000 degrees of free Celsius, concentrated on that very small bit of ceramic plate. Now, we think of concentrated solar. How many of you flown to Las Vegas and seen those towers out to the right? Those are molten salt towers at the top. So we're using the concentration of these massive, expensive parabolic mirrors to concentrate the sun's power to melt the steam is kind of inefficient means of storing heat. It'd be better to melt some kind of salt. But this isn't meant for the production of electricity. You only need 100 degrees Celsius to make steam, which is kind of inefficient. You really want steam under pressure. So for that, you need maybe 500. 500 Celsius is really good, and that's what you can get. But with this, to get this higher degree of precision, this company is achieving it with inexpensive flat mirrors. So instead of the complex parabolic mirrors with a more advanced control system, they're able to get this company is able to get this kind of production value out of this because of those cameras at the top and a lot of compute. So they've exchanged this, this is literally November 20th of just last month. So they've been able to take these mirrors that are controlled through an interactive, complex, high-speed control loop to analyze every mirror to keep that concentration of solar power on that spot. This is interesting because it's localized heat, not for electricity, but for the generation of something like, 20% of all the CO2 emitted in this world come from heavy industry. Half of that is for the production of heat, where we take coal, we burn it, make a really hot furnace to make concrete or to make steel or for some kind of chemical process. And if we could take just that 10% away, cars only account for 6%. So 10% is just to make heat, to make the things that we use to drive, like the Tesla, to make the steel. But now you can do that on site. Now, what I found interesting here is two things. Number one, I didn't know that at 1500 degrees you can combine H2O and CO2 to make syngas, or a synthetic fuel, which is amazing. So if you get to 1500 degrees Celsius, you had a really cool spot. As long as you're not putting more energy into the system, you create basically free fuel, which would be amazing. It would mean that the gap in our goal as a society to prevent the problems we're going to have with this climate emergency, this might be a way to it. But I'm a programmer. That's my background. I'm a software engineer. I would have no clue how to help here. It's actually the reason I'm here at Microsoft, because I feel like I know what I'm doing programming-wise, but when it comes to electrical or mechanical engineering, I don't know. I don't know how to help. But I do know a little bit of reinforcement learning to be dangerous. And I know that I can help teach this system, or teach the mirrors to point and keep that concentrated heat in the right spot. This is not our customer, by the way. This is literally, I have no idea how they're doing this. They might not be using RL. It's just now that I'm in this space, I see everything through the lens of a mechanical engineer or an electrical engineer. And so what reinforcement learning has done as a technology, and I'll kind of explain where we're going with it, it's caused me to think as a programmer, how can I join forces with mechanical engineers to affect the world, the physical world that we live in? The best minds of our generation are being focused on getting people to click on ads. And I feel like as a software group, maybe there's something we can do to affect the physical world. And I think we can do that through industrial reinforcement learning. So what we're trying to do is figure out how to teach machines to benefit us. And we're using teach in a very specific way. I'm going to show you this little thing later. The math behind this is like entry-level mechanical engineering. The math behind making this little thing stand upright is frightening. It is not for me. Any mechanical engineers here? Or control engineers? Do you remember inverted pendulums? Do you remember the inverted pendulum problem? We'll cover it. I will be a refresher for you, but I might be calling on you later. So I work with mechanical engineers, electrical, physical engineers, physicists, chemists, PhDs, because we're trying to figure out how to combine the smarts of software to solve problems in these areas. And although we're currently focused in this industrial space, it's really around three broad problems. How do we control, calibrate, or optimize systems, either a mechanical or an industrial system, to benefit us? So in the case of that solar system, it was continuously calibrating the concentration of its heat to achieve that goal, and that was 1,000 degrees Celsius. In the case of the Tesla, it's constantly controlling the output of the car based on the sensors that are coming in. So those three areas, calibrate, optimize, what was the other one? Control. This is control. So these are areas where I think where we can apply really current reinforcement learning or machine teaching concepts to benefit us. Now, this is when Scott introduces the slide that takes us from 1868 up until 2019 in just 3 pictures. So if you go to Wikipedia on control theory is the really nerdy math part of engineering. The head of Microsoft Research has a PhD in control theory from Carnegie Mellon. And he just announced his retirement, Harry Shum. Control theorists, I work with a few of them. They build systems to control machines. The first example of how we controlled equipment is not the steam engine. It's what controlled the steam engine. And that's called a mechanical governor or a centrifugal governor. And it's the coolest thing. I don't care about the other 2 sides. I'm gonna show you this. This is James Watt's version. So, Watt was really obviously influential in bringing us the steam engine, but James Clerk Maxwell's equations, electricity and motors, he was the one that he had a paper, research in the mid-1800s on governing systems or controlling machinery. And that's when he came up with this concept of a feedback system to control a steam engine. So the thing on the left, this is definitely a case where some YouTube will help, because it's much more interesting to explain how this thing works. Wait, I've got this fancy touch bar, and it doesn't work. There we go, in show. Okay, where's my video? There we go.
And run it. And I've just got it running off my 20.
So he's literally burning wood to create steam, and the steam is used to generate pressure in these pistons to drive this belt. The belt has a giant inertial system, so it's a heavy mechanical system, but in order to keep it from running away and going too fast, you have that little spinning device at the top. The phrase balls to the wall, as crude as that sound, actually comes from this thing, because when the balls were all the way out, there was too much load on the system. And as you spin it faster and faster, the balls travel up and compress a spring, the spring being the program, but essentially it's a constant that's used to govern the amount of steam that's let into the system. So as think of a figure skater. So if you put your arms out, you slow down, you bring your arms in, you speed up. In this case, if the balls move out, then the system's going too fast, you can slow it down, reduces the amount of steam. This is important because in England, they were using steam engines to drive mechanical looms. And so when the looms come online, these little tuning systems would slow it down or speed it up. So it's the smallest, geekiest thing that's kind of in the background of our consciousness. Like, have you guys seen this thing before? I didn't really know how it works until it's literally the first paragraph in control theory. So you don't have to go far to find it. But the modern equivalent of this system is called a PID controller, or a PID controller. And I'm going to give you an example of a PID controller on the system here to the right when we come to it, but I'll show you how we've come from the far left to the right. Now, this middle block is the kind of automation that we think of when we think of a controlled factory. So when you have everything kind of nicely lined up, you have big mechanical arms taking steel or doors from an assembly line and putting them on a car, you're in a walled-off position. The robot is not, they're big, dumb, and repetitive tasks, things that humans would be either slower at or unsafe. Now, going back to the steam engine, there's a group that was led by a guy whose last name was Ludd, who kind of led a revolt to the people that were being put out of business as the looms were mechanized. And there was a group of people that were actually persecuted a lot, like put to death for smashing the mills. And that group became known as the Luddites. So there was a lot of resistance to this kind of change. I don't think now, looking back on it, there are clearly parallels now, and I'm sure we could talk about how computation or automation might be taking jobs. The jobs that we think they might be taking are the ones we don't want to do or aren't lining up to do it. The healthcare crisis in Japan. They have such an aging population, faster than most countries. They have a real problem, and we think there might be some applications of automation and robotics to provide some healthcare there. One of our customers is delivering solar panels autonomously. So they have an autonomous Bobcat. So you think it's scary driving a Tesla for the first time. Imagine a Bobcat coming at you with forks. And they'll go to the back of a pickup truck, back of a semi, a flatbed, pull the solar panels out and deliver them just in time to a worker installing in the field. So this is real technology that's working right now. I talked to the people that are working on it. Mitch said they can't find humans at 15 or 20 bucks an hour just to sit in the cab of the Bobcat for 10,000 hours, which is what's necessary for this thing to qualify to run on its own. So they have the technology. They can't hire people just to sit there. Granted, it would be a pretty boring job. But you could sit there like in a Tesla and just kind of zone out and maybe hit the button if you're about to hit a person or a tree. I don't know what's in a solar field. But they can't even find the people to sit there. Chris, I'm going to use your example of the garbage truck. And I'm going to steal your slide. Chris and I were talking about this, and it was a photo, 4 photos. In the upper left-hand corner was the kind of garbage truck that I grew up with, which is a really weird sentence. But there was one person driving and two guys in the back that would hop out at every stop, grab the cans, get them ready. And then it became two people. And then it became one person. And then one person's driving. Do any of you have the garbage truck where the arm goes out and grabs it and empties it? So for the transition from 3 to 2 to 1, it's not like people, I mean, look, you're gonna have that one job, but the other two are doing something else. But that is a certain kind of automation that is coming, or we can enable. Not necessarily a job that people might be sad to see go. There is a great video, by the way, of that thing freaking out and like shaking a trash can. I love it. Okay, so let's talk about the right side, autonomous systems. So this is a case where we think we can control machinery, we can build systems that can operate in an environment that's highly variable or changing. And this is where the questions like you just talked about the Tesla and autonomous driving. Yes, autonomous driving is massive. Half of Berkeley AI research, Bear, we're located over in Berkeley, across from UC Berkeley. We'll be co-located with Bear in the same building when we move over in January. I would say about half of the research coming out of that group is around their autonomous driving platform. NVIDIA has a massive effort underway with their chipset and their simulators to really push the envelope on driving. But we believe we can take autonomous systems into other directions beyond driving. And that's what I'll be talking about. It still requires a lot of the same reinforcement learning or sensor-based systems, but we're going to look at it more from a mechanical system. This wind turbine is how I got recruited to Bonsai. A friend of mine, Cyril, who's on the Bonsai team, Bonsai was the acquisition of Microsoft about a year and a half ago, and that's the company in Berkeley. So we're now called Autonomous Systems. So be more to it. Bonsai is a little bit easier to remember, but that's where this came from. So about 3 years ago, I saw an example of a wind turbine modeled and simulated in MathWorks, particularly MATLAB and Simulink. Are any of you MathWorks engineers? Wow, it's really hard. It's hard. Well, for me, it was incredible. So he brought this thing up. It like double click, check this out. Oh, it's a wind turbine, and he kept drilling into the whole system. The ailerons, the entire control and the energy generation system was all modeled in this one place. And he said, now you can have sliders to kind of make the thing turn and make it go, but how do you control it to do what you want? How do you control the downstream wind turbine that's affected by the propeller wash from the one in the front to know when should we, with this wind that's coming up, do we want to turn into it? Can you get some kind of sensor data from the ambient surroundings to try to better tune your system? Also, those blades are really big and expensive, and they will break. There's a whole business just around the autonomous inspection of the blades, which can be driven by drone systems. And so it's a really fascinating nexus, and I was so captivated by how we could come out of, at least the computer science world, could come out into the real world and affect these physical things. So that's where some of this information is coming from. We have some demo, there's a demo on here. I love these 3 little demos, and I'll click on the building one. When I first saw this, I was like, all right, this looks completely fake. The data behind this is actually real. In fact, there's a CSV file that's been scrubbed from the real system that we taught. So this is an example from Schneider Electric, and this was a kind of a shootout between a reinforcement learning system. You know what? I've talked about reinforcement learning and not explained what it is. I am sorry. Yes, it's like, okay. A guy by the name of B.F. Skinner. Any psychologists here? Yes. You know what a Skinner box is? Someone's nodding their head in the back. A Skinner, you've all seen one. If I put a rat in a cage and gave it a treat when it hit the button when the light turns on, it gave a little treat, I am conditioning a response. And I'm reinforcing a behavior. In this case, it's a positive behavior versus being punished for it through an electric shock. So that conditional behavior was what we take for granted now, was a new concept. We thought before that all behavior was learned, or not learned, but can you help me out? Inherited or innate? Good, yes. not able to be conditioned or reinforced. So we also think that it's a model of how humans learn new concepts and new systems. So you can learn something by being shown an example. We're really good at mimicry. So here's an example of some behavior I want you to do, and then I could show you to do it. And so later I have an example of that. So I think now the concept from different areas of focus, like from psychology, Marvin Minsky first talked about reinforcement learning along with his colleagues back in the 60s. So this has been around for a while. What we're trying to do in this case is not reward a human, but reward a computer, reward a system to find, will that just keep going up and down? It's kind of cool, I don't know. It adds some, yeah, it adds some drama. Yeah, so the analog here, like see all those video games? Okay, so imagine one of them is Breakout, like the classic game Breakout. Well, classic for me because I think I bought it. I didn't buy it, my parents bought it when I was in 7th grade on the Atari. But you know, you got the little paddle and you can move it back and forth. And your goal is to get a high score. And so I can see the state of play and all I can do is go left or right. If the ball goes through, I've terminated my turn. Okay, so you can sense, plan, and act in such a way that rewards you for the best behavior over time. That's reinforcement learning at a high level. It literally is that sense, when you sense the state of something, you terminate your session, you get some kind of reward for doing the right thing, and you have some set of actions that you can perform. We call that STAR, state, terminate, actions, and reward. And we have a file called star.python, star.py, and it's literally those functions, and it's how we start to build, using a language called Inkling, to model the system to try to teach the computer what to do. It's like, look, just get a high score. That's it. Like, you can teach a computer how to play Breakout just by looking at every pixel on the screen, and we can do that with GPUs, and somehow parsing the high score, and somehow let the computer go left or right. Now, your first policy can be random. Literally, just pick a random number, flip a coin to go left and right. The real art is determining the right time to go left or the right time to go right with the paddle to get the highest score. So that's reinforcement learning in a nutshell. It's, on the surface, I came from a background, my more project before that was around supervised learning with gradient boosted machines. And I thought, wow, it's just STAR, that's easy. You know, that's a pretty easy concept. This should not be a difficult job. It's been really hard because of MathWorks and Simulink and mechanical systems and error and feedback and friction. So the physical world part has been challenging. This is an example that's even a little bit more difficult because we're in the case of Breakout, which, by the way, was solved with an algorithm called DeepQ Networks, or DQN. And I think that paper was, I think that was 2015. It was, or 2014. It was fairly recent. So just like supervised learning, we're able to go far with supervised learning because the abundance of data and the processing with GPUs, we need the same kind of GPU processing to help find the best policy, to basically build. Go back to Breakout for a second. If we're building a neural network, you have 2 neurons as your output. It's just a category. Do you go left or right? So you have 2 outputs. Which one lights up could be, what is it, argmax? I forget what's it called. You're trying to choose between 2 of the higher numbers in a neural network. The input is every pixel on the screen, maybe RGB. And what you're trying to do, your objective function is to get the high score over time. That's a little bit harder. Because in the case of, like in AI, we will start with the iris data set. So here's 150 flowers, and I'm giving you 4 bits of information on each flower, the length and the width of the stamen, and the length and width of the pistil. Determine if it's one of these 3 flowers. Setosa, this would be a great interview question for statisticians or reinforcement. What are the 3 species of, Setosa, Verga, I forgot what they are. From those 4 things, you just have to decide what flower you're looking at. Now, in the case of like Breakout, you have to decide which direction to go. But when you make a move to the right, and you die like 5 seconds later, how do you know that was the wrong move? This is a fundamental problem in reinforcement learning. It's a really, really thorny problem, and it's called the credit assignment problem. I'm going to give you an example of how this is difficult and why, and the attempt to solve it. There's another concept besides STAR called the exploration versus exploitation phenomenon. Exploration versus exploitation. And this is really awkward because you're here, but I've talked about this a lot. My wife and I have a favorite Thai restaurant called Boa Long in Albany. And I'm like, okay, we want Thai. We're going to go to Boa Long again. At what point can we try something new? How do we know that there's not a better global maximum or local minimum of a better Thai restaurant out there? And so the way we solve it in RL, this is because you don't want to get quickly stuck on on what you think is the best Thai restaurant until you've kind of exploited more options. And once you've exploited all the restaurants, then you start, once you've explored them all, you start exploiting that really good, they do have a good, the pineapple curry chicken, oh God. So what you do, you start with a number like 30%. You have a 30% chance we're gonna have dinner someplace else. And if it's better, then you stay there for a while, but now you've dropped that 30 to 20, and you keep lowering that percentage chance. So you give the computer a way to explore using it, we call it epsilon, of exploring and exploiting new results. So let's say I just got lucky with Breakout. I jammed the paddle to the right, and I happened to get a good score. Well, next time it's like, well, last time I just go to the right. But you still need some kind of like Markov chain disturbance, some kind of stochasticity to make sure that you can maybe find and jump out a better place. So the combination of those two, that's kind of the guts, exploration versus exploitation in STAR. Now, to bring it way back up at a higher level, I'm going to give you an example of trying to control or optimize a system that would be classically very difficult to do with programming. So this is an HVAC system. I feel like the screen's going to come down on me. Where we have 3 competing optimization goals. So occupants in a building, like it feels like it's about 75 degrees in here. It's a little warm. I'd like it to be cooler. And somewhere there's an Outlook calendar that knows how many people are in this room. And we're all 90-watt generators of heat. So maybe it should know that and maybe put on the AC earlier. But there's a certain amount of OSHA, there's an OSHA standard of fresh air that needs to come in. And of course, Microsoft would probably like to spend the least amount of money on electricity. So you have these 3 competing optimization goals. And how do you build a system to read from these sensors the state of the world, the current cost of energy, the time of the day, the outdoor temperature, so over time, it can learn to find a better policy, to know when to turn on the HVAC. Now, in this case, obviously there's a lot more detail behind here. The key number is poorly rendered in this HTML. But we met the temperature control goals against the hypothesis, the null hypothesis. We met the air quality standards for bringing in fresh air from the outside, but we're able to save 20% electricity over the existing system. So remember what I said earlier, how like the big consumers of electricity, buildings and HVAC systems are enormous. And if there's a way to get 20%, you have a difficult infrastructure problem because Johnson Controls or Siemens or these other systems control all this. They're kind of in the past, and the way to kind of bring in these multiple sensors will be tough, but then you can write an overall higher level policy to potentially get to a better solution. So we have we have a couple more of those examples there. Let me go back to the slides, because eventually I gotta get to that. Okay, so I talked a bit about deep reinforcement learning. We have a model of a system. In this case, is a simulation down at the bottom. And this overwrought electronic brain really is supposed to emulate this policy. At the end of the day, there is a neural network to make the decision as to what to do to gain some kind of advantage on the system. So we have found there's 3 areas where reinforcement learning really shines. One is in its ability to its adaptability to new scenarios. The best way I can explain it, there was a TechCrunch robotics conference about 8 months ago at UC Berkeley, and I talked to this guy who's doing some autonomous robotics. He said, it's not hard to get 90% of the way there. a few smart electrical or mechanical engineers or some programmers. It's that last 10% to close the gap between, and then he drew this picture. He said, look, let me draw a really simple physical system. You have two axes. The goal is to build a model of the world in this, whatever the scenario is. Let's say it's like temperature over time or whatever. He drew an X in the middle. He goes, that's a sweet spot. That's what the real world at this particular point wants. And you can build a model that's 90% of the way there. But that last 10%, if it's not there, it's going to fail. In the case of those mirrors, maybe they don't line up and you don't hit that critical temperature threshold. In the case of the Tesla, if the model's not good enough and you can't generalize, you can't recognize a new scenario like the double yellow lines. In our case, the adaptability is only limited by compute time. There's the business model, training. How do you train these models? To where you could take sliders and discover a better policy to control a system by changing and varying its inputs in a simulator rather than doing it in the real world. I have this little device up here we'll talk about. You can train it in the real world. It just takes forever because it's a real physical thing. I'd rather train it or learn more about it in a simulator. The ability to adapt to multiple goals. That was the example of the HVAC system. And finally, the operator overload. I actually remember the very first video game I ever played. It was by Chris, what was his name? Chris Crawford, yeah, thank you. It was SCRAM. And it was a game that was inspired by the nuclear reactor meltdown at 3 Mile Island. That's a great game for a 7th grader. And it was the weirdest game. You're presented with this giant control panel, and this is so apropos now because of Chernobyl. Great show. So you're presented with this panel, and they simulate some pump failure, and you have to keep the reactor from going critical. And so you can scram the control rods, which you drop them in to stop the reactor, or deploy people to fix the pumps, but then those people in the game always die. So you have a fixed number of resources you can deploy. Like, it's a really hard game. I was terrible at it, and I'm surprised I ever played another game because it was not a great experience. We actually found the game. John found the game, and at some point, we're going to port it and see if I can learn it with RL. It's so the operator overload concept, I think, is something. I think this is where AI can maybe not make the decision for you, but help point you in the right direction. My cousin is a bread factory plant executive. Like, he literally makes bread at a very high scale. There's a good chance if you had bread today, well, most of the bread that you see in the stores are made by just 2 or 3 companies: Pepperidge Farms, Flowers, and Bimbo Group from Mexico. He works for Flowers. I've been to their factory, and I grew up, I love the Canadian TV show How It's Made. I love assembly lines. And so watching those things and being able to walk through a real system, and he said, at the end of the day, they have product. That's what they call it, by the way, HFCS. High fructose corn syrup comes in 55-gallon drums. So we have all the product coming in here, and out the other end is bread going on a truck. And in between, you have yeast making all this stuff work. And so although it's a big factory, they have living things in the system trying to control it. And I asked him recently when I took this job, I said, when the system doesn't work, what do you do? He goes, well, we have these kind of experts on staff that they kind of know it. And I said, well, how long do they have to be there to learn it? 20 years? And a lot of times there may be kind of a playbook, or they'll just say, I don't know, let's try that. And so they're just trying things. And so if there's a way to codify some of this intelligence, especially in the world of civil engineering and our aging infrastructure, if there's a way to augment the kind of understanding about how our big critical infrastructure systems are failing and capturing this intelligence before these people retire, this might be a good way to help manage some of these systems going forward. I got 15 minutes. All right. I'm going to, well, this will be the last slide. I'm going to jump to demo. I did say, how many of you know the story of the defeat of Lee Sedol? I don't know if I'm saying his name right. The Korean Go champion. Yeah, it's fascinating. I played Go in college, and I was terrible at it. But after 6 months, I could beat the best computer game. I know, because I had it. And it was trivial. I mean, I was really, really bad, and it wasn't hard to beat the best the best computer player. And when Korea broadcast this kind of winner-take-all over 5 games back in 2016, they had a live viewership of like 8 million people. It's a very big game. The state space, if you never played Go, it's an easier game than chess in terms of the rules. A 19 by 19 grid, you play stones, you alternate turns, and if a stone, if they're called eyes, can be circled, then you've captured it, you've taken those stones away, and that's how you earn points, you capture. But it's not a hard game like chess where it's all attack. It's a balance between defense and offense. It's a really subtle game, and Lee was the best player in the world, and he retired. He retired after losing 4 games to 5 against OpenAI. It was OpenAI, yeah. DeepMind, God, I'm sorry, David Silver, DeepMind. His first game, I think he played a little loose and was surprised, like, I'm really gonna have to play this thing well. The second game playing the computer, you can Google Game 2 Move 37. Game 2 Move 37, the computer played a move, and the commentators, like live on a board, or they're putting them, he went back 3 times, like that was a mistake, what's going on? The computer played a move that was so mind-blowing that it changed the way Go was played. It is changing Go, and it's changed reinforcement learning. It's shown that through a lot of compute power, and Wired estimated it was $35 million worth of computation, because the state space is 10 to the 170th power. The number of possible games on the 19 by 19 board with the 2 players. 10 to the 1, that's more atoms in the universe. So it's a very big game, but you don't have to explore the whole space. But when it played that move, later Lee said it was like playing an alien species. He saw this thing play a move that no one else would have done before, and it turned out to be a brilliant move. And later, it informed him about how to play differently as well. And he played a move that he said he never would have done before, or it was just a very aggressive move, and it was just fascinating. So I love the fact that games are being used to push the boundary of what can be done with computation and AI around chess and Go, and I'm a StarCraft player. There's Dota out there, and there's systems that are being put together to beat multiplayer cooperation. OpenAI just published this beautiful rendering and this game of hide and seek, and showing the collaboration between the hiders and the seekers, and collaborating around the placement of blocks of wood to block. It's the cutest thing. It's like Baby Yoda, but for RL. And it's these 2 little players that are given a head start, and they're green, and they run into a room with 2 doors, and they find these wooden blocks, and they've learned to go put the blocks in front of the doors to block the people from coming in. The red team. And then the red team, their eyes open up, and they go look for them. If they're found, the game's over, and they start over. So what we're learning here, though, is not just how to Go, where it's one human versus computer. It's this more emergent behavior of how 2 systems these 2 different agents can work together to maybe discover some new behavior. It's actually a great way to find the limits of a system, because the seekers found that if they pushed the ramp into the wall, there was a bug that would launch them over the wall into the room that the hiders were in. So it's really fun to see the edges of where AI is finding our exploits. It's exploiting, given enough time, it will find ways to exploit behaviors that we weren't expecting. And we're like, oh yeah, I should do that instead. I'm going to show you this little red box up here before we run out of time. So it's time for the broom. My cousin and I used to play a game where we would see who can hold this broom up the longest. Has anyone done this before? Well, actually, who's not done this? You have not done this. Can I teach you? Okay, so here's the goal. It's to balance this broom at the end of your hand without falling on the audience. I'll go first. Honestly, there's probably liability somewhere, so I'm going to move.
Give it an umbrella policy.
Yeah. I first did this with a 12-foot aluminum pole at a conference that they used for scaffolding. And it was fine, and then I went to go set it backstage, and 60 seconds later it fell. So I don't know what happened, so come up here. So. So if you hold this thing like this with a mass at the end of a moving pendulum, well, it's called a pendulum, and they're easy systems, easy. In my high school physics, it was a frictionless pivot point up here, so it would go forever. But in the real world, there's friction, and this will slow down. When you invert it like this, now it's a continuous control problem. So you can't take your eye off this. You have to keep looking and sensing where the top of that is and acting on your hand. So think about star. So it's the state of the system. There's 4 numbers that, well, really 2 things that tell you about the system. There's the position of the thing up top, and ideally you want it at 0 degrees. Let's call this 0, and this will be 180 degrees. So you want to keep it at 0 as long as possible. And I kind of know if you get it to about here, at more than 20 degrees in either direction, it's going to fall down. And also, there's not a lot of space, so I'm only going to let you go like a foot or 2 from left and right. Now you've created something called the cart on a pole problem. So, I'm sorry, a pole on a cart. And there, how many of you have been to the Exploitation? It's the very first exhibit. The very first exhibit when you walk into the Exploitation. It's on your right-hand side near the drinking fountains that are in a toilet. And the kids love that. And there is a mechanical system where it's trying to balance a pole on top of an object that moves left and right. And it's a hard thing. But you can think about it. There's only 4 numbers, right? There's the position at the bottom and its velocity, the position of the broom and the theta, the angle at the top, and how fast it's going. That's it. There's only 4 things, and you can only go left or right. So you have your state space, your actions. We know what termination looks like. And a reward is how long you hold it upright, okay? So imagine this concept now, but done in a rotary fashion. That's what this is. This is a Kwanza Cube. It's a really straightforward device. It's this box with the USB and power in the back. There's a little rotary wheel on the top that can go left and right. If you apply 3 volts, it spins with its maximum torque to the right. Negative 3 volts goes to the left. It's a real valued number. And the goal of this is to build a system to where the inverted pendulum, in this case, this aluminum rod, oh yeah, you can do this. You can show this. In this case, the goal is to make this thing, spin it back and forth enough to make it stand upright. This you cannot do you just can't do this by yourself. Like, you need a system to do this. Like, even if I just kind of spin it like this, I might get it vertical for just a moment. That's it. Now, this is not a motor. This is a position. This is what's it called? What's the tech here? You're the electrician. What is this? Sorry, the electrical engineer. By the way, if you want to piss off an electrical engineer, call them an electrician. It's a rotary sensor encoder. Thank you. So if I put this here with these really expensive magnets, and I can attach it so we can ask it what its position is. And I have learned, and I set that up here. Wow, that's a great camera work. Does it kind of work? I have a little Python program here. Let's see if it's behaving. I can control this system with this joystick. So see if you can get, maybe from the top down, I don't know. I've gotten pretty good at this. So I'm just using the thumbstick, going left and right, to get it to stand upright. Now, that's about as good as I can get. It lights up like that at the top when it gets close. Okay. So for the mechanical engineers, right, it's called an acrobot. And there's really 2 policies here. One is an energy minimization policy that's required to get it to spin up. And once you're within about 20 degrees to the top, you flip into a PID control system where you're using 3 numbers to, you're looking at a gain offset, an integral, and derivative of your error so you know where to move the motor. And for that, I just have to press A, and it'll do it. I wish I could say I wrote that. So there's a young man who goes to University of Calgary. Kirill is going to be presenting a paper on this at NeurIPS. So this is not AI. This is mechanical engineering, and it's the best this particular system will get. It's cool. Actually, I'll leave this running when we're done, and you can come up with the controller and try to see if you can spin it up. But it's wild. If you knock it down, it'll just go back up. Okay, that's a well-known system. I asked Kirill, how long did it take you to code that or understand it? He goes, well, you need a 4-year mechanical engineering degree, and then you need these 2 special classes on control theory. It's a lot of work, and it's worth it. This as a mechanical system is incredibly simple. The inverted pendulum is easier. Cart pole is kind of in between. This is cart pole, but in a portable package. This is also $5,000. So I'm very careful about it. So when you come up, just be gentle. Yeah, it's a lot. But it's really, the woman in the video, Nissa, the electrical engineer, I'm working with him to build my own thing, which maybe we'll talk about later, like in a year, because this is kind of expensive. She's like, $5,000, I can do it cheaper. Then she felt the bearings and the grease on the bearing. She goes, oh, it's $1,000 of grease right there. It's a really good system. Now, I don't have a mechanical engineering degree, but I can teach it. So, well, let's compare that policy with the reinforcement learned policy, which is this. It's not bad. It's very good. It's a little shaky. This is the Chihuahua version, because I'm not done. This is observing 4 states. Alpha, which is the position of the motor, the alpha velocity, theta, which is the position of this rod and its velocity. I only have 2 actions, but it's continuous, -3 to +3. And the reward is just stand up as long as you can. Now, my model, I have a software version of this, which is how we taught it. In fact, you can steer the software version, the simulation, and that's how we taught the system. I can toggle, I can turn it off. I'll also tell you there's a cheat mode. So if you press Y, if you get close by hand, eventually it'll stand upright. Wait. Oh, Saya's here. Oh, there it is. So that's the cheat mode. So what you saw there was an example of a classic mechanical solution, kind of a PID-based energy control, but a taught system using reinforcement learning and our tools, machine teaching. That particular looks like this. Oh, let me thank you. That's excellent camera work. Thank you. How about a hand for Joshua? Come back. 2 minutes. Yeah, I just heard the alarm. Yeah. So I'm not going to go through the whole teaching bit, but I'm going to show you what some of the code looks like. So this is the Bonsai platform. This is the hello world in control theory or control mechanical engineering. This is something that you would not use RL for. This particular example. We want to do as good as we can as a classic engineering control and then go beyond what it can do. So this is a limited platform. There's only so much you can do, but it doesn't take much more to start to find an example or scenario that's nonlinear, or maybe, like if I swapped out this bar for a shorter one, or changed the weight of it, or put it somewhat sideways, this classic PID-based system will not work at all. But if I have a simulation of that system and I've taught it with RL, then I can simulate those different, change the friction, change the length of the pole. I can change gravity. I can put it on the moon. Like, how would this look on the moon? I'm going to give you a link at the end of the talk where you can spend a couple hours with me and John, not together, on Teams. We'll walk you through some hands-on with this product, but it's a 2-hour session. But part of it at the end, you teach this, not this system, but a slightly different version, the cart pole. And then at the end, we're like, oh, we have a brain. Let's see what it looks like if you change the gravity constant divided by 6. So you can see what it looks like on the moon. Or change some other physical factors of it and retrain it to get that kind of breadth to get the adaptability. So this is an example of this is what the UI looks in the product. You can see we defined the state of the system. I mentioned the theta and theta dot. And our action space is -3 to +3 volts. We have the simulator is here. Wait. I can send a link out for the code for this. Joshua. Yeah. we'll add that to the link. So I can send out the code for it. So you can follow along at home.